you guys, so we're going to continue chapter 4. Before we start going into the actual model that we have, the quantum model, I want to do a brief little atomic history from chapter 3 so we could get the visualization of what atoms started looking like and when they started looking that way. So the first thing is first is we have Democritus. Democritus was in about 450 BC. Okay, we had Democritus. Now, Democritus was not a scientist, he was a philosopher, and he said that the all matter, is made of tiny, indivisible little particles called atomos. Atomos. So everything was made out of solid little tiny particles called atoms. Okay? And this just came from a philosopher back in 450 BC, right? You could get something and cut it until you could no longer cut it. And when you reach the point where you can no longer cut it, you have reached an atomos. All right. This then many years later led to some more discoveries. So we have John Dalton, and he was about 1800s AD. This is about 1800s. Okay, and John Dalton came up with the atomic theory. So in the atomic theory, he said all elements are composed of atoms. Atoms of the same element are identical. He said that you have the law of conservation of matter. So what you start off with is the same as what you end with. Okay. And the last one is that compounds develop in fixed ratios, right? So they have fixed ratios. Okay. So let's put that in a nice little drawing that we could kind of look at and relate to. So let's use red for hydrogen. So when you see a red dot, that's going to be hydrogen. And let us use blue for oxygen. So when you see a little blue dot, it's going to be oxygen. And actually, oxygen is going to be much bigger than hydrogen. Okay, so remember, Dalton said atoms of the same element are the same. So atoms of different elements are obviously going to be different. So these two are different. So we still have indivisible particles right here. Okay, and when they combine together, they're going to combine together in fixed ratios. Now, we know that hydrogen is diatomic, so that means it comes in twos. And oxygen is also diatomic, so it also comes in twos. Now, I fill them in because they're going to be solid spheres still. Well, we haven't had the microscope technology to figure out what's inside an atom. All right, now they're going to go ahead and combine together. So this is similar to the example we did in chapter 3. When these combine together to form water, you're going to get your oxygen in the center. And in a fixed ratio, they will form water. Just like that. All right. Now, if we want to continue going into Dalton's next one, which was the law of conservation of matter, we could start balancing this out, right? Because obviously we have one oxygen left here, and that doesn't really balance everything. So what we're going to need to do is we're going to need to figure out a way to make sure that we have everything nicely balanced. If I have two oxygens here, that means that I'm going to end up with at least two waters. And you're going to say, well, how do you actually end up with two waters? You don't have enough hydrogens. Well, that's because we're going to be adding another hydrogen molecule here. So now we have two diatomic hydrogens, and I'm going to go ahead and make mine. water there. And now everything is perfectly balanced, okay? So a total of 4 hydrogens plus 2 oxygens gives me 2 waters. And to put that in plain English, I have 4 hydrogens plus 2 oxygens. That's going to give me 2 waters. All right, now that's not how we actually write it, because you notice that these are diatomic. And when we write something in diatomic form, it's not going to look like this. This, I'll cross it off later, is incorrect. So you actually have diatomic hydrogen, H2, that's what we started with, and you have 2 of those, plus 1 molecule of oxygen, and it's diatomic, and that produces 2 molecules of water. And water is made out of 2 hydrogens and 1 oxygen, just like this. So if you were to write your equation like this, that would be incorrect, right? And this would be the correct way of showing the law of conservation of matter and writing your correct balanced equation. Okay, moving on from that, okay, after John Dalton, we had a couple of other scientists. We had Faraday, and he was around 1830s, and he actually discovered that atoms have electricity. So basically, here's my atom, and he goes, I don't know how, but atoms have electrical charges. So they have charges, and I don't know how to draw like a charge here. So I'm pretending that that's charges, okay? Electricity, right? Running through them. That's what they have, running electricity. Okay. So Faraday discovered that atoms are electrically charged. From Faraday, we then have J.J. Thomson. Actually, let me do that one here. J.J. Thomson. And J.J. Thomson made a huge discovery, okay? Huge. Now, his model from 1890, it was like 1898 or something like that, so the 1890s, is actually the most accurate model to our actual model that we have. Like our actual model is called the quantum mechanical model, and J.J. Thomson's model was the best representation. Okay. Well, we obviously didn't go with J.J. Thomson's model. We started teaching the Bohr model because we didn't know and understand the movement of everything until much later on. So J.J. Thomson's model is going to be called the plum pudding model. And he developed this plum pudding model basically by discovering that atoms have electrons. So he used the cathode ray tube experiment. And in the cathode ray tube experiment, he threw gas inside of it, and he noticed that certain particles were going straight for the positive end, right, of this tube. And discovered the electron, and he actually discovered the charge of electrons as well. So this discovery, so the cathode ray tube experiment, led to the plum pudding model. So that's actually right. The plum pudding model, and that was actually the name of the model. And he basically said that an atom has a positive inside. So I'm going to say all of this is positive. So everything that's in this brownish color is positive. Okay. And the plum pudding model, some people actually call it like the chocolate chip cookie model, things like that, because it's easier for us to think of it that way. And that inside of the plum pudding model are going to be the electrons just floating around, randomly moving inside of the plum pudding model. Okay, So in it, you have electrons. So it's a positive, this part is positively charged. So a positive atom with electrons freely moving inside. Okay, so J.J. Thomson's plum pudding model. All right, now J.J. Thomson's plum pudding model led to, which one did it lead to? Millikan's discovery, and Millikan's discovery was still with the charge of the electrons. He basically just built off of J.J. Thomson's discovery. The most significant one, though, after J.J. Thomson was Rutherford, Ernest Rutherford. So let's go into Ernest Rutherford. And Ernest Rutherford developed an experiment called the gold foil experiment. I forgot to spell his name. All right. Don't quote me on the spelling of his name. I'm pretty sure it's wrong. All right. So Ernest Rutherford. Ernest Rutherford. All right. And his discovery was literally shortly after J.J. Thomson's plum pudding model. And he said, using the gold foil experiment. So he had the gold foil experiment. Okay. When he did the gold foil experiment, he discovered a lot of things. And in his discovery, atoms have a center, and this center is called the nucleus. And surrounding the atom, okay, somewhere in there is going to be your electron. So the nucleus, he says, is positive. I'm going to just do that right there. Okay? And then the rest of this is empty space. So we have a positive nucleus that is dense, okay, and holds most of the mass. So now not the entire atom is in positive, just the nucleus. And then here we have the electron orbiting the nucleus. We have the electron orbiting the nucleus. So this is Ernest Rutherford's model, and we call it the nuclear model, okay? So this is called the nuclear model. Nuclear. All right. The nuclear model then had further developments by Moseley, but then most importantly is going to be the Bohr model, okay? So the Bohr model, which is the model that we study, very similar to Ernest Rutherford's model, except that now these orbits have a quantized amount of energy, okay? So we still have a nucleus, okay? And by the way, Moseley discovered the neutrons. So I left Moseley out on here, but if we want to put Moseley, he did neutron discovery in nucleus. Okay. I don't know what year he did it in. Okay, so anyways, we have now the Bohr model. This is sometime in the 1900s, probably 1920s, I don't know, early 1900s, okay? That's somewhere between 1910 to 1915, all right? This model came out. Okay, so in the center, we're going to have our nucleus. And then around this is going to be our orbits. And these orbits have a specific amount of energy associated with them. Okay, and in it you have electrons, and he discovered that the first orbit carries 2 electrons, and that the second orbit carries up to 8 electrons. And then you could have a third orbit going through. Now I'm going to just do like half an orbit here because I don't have space. All right. So you have your first energy level, second energy level, and your third energy level. Okay. And so these are going to be called energy levels. Energy levels. Okay. The higher you go, the more energy something holds. In this case, this one right here, we said that this is called the outermost shell, which is the valence shell. And it carries the valence electrons, and those electrons are the ones responsible for bonding. Electrons in the inner shell are not responsible for bonding. However, they do play a big role when it comes to our electricity, which is this chapter. Okay. All right, so there's our Bohr model, and in here, remember, we have the protons plus neutrons. And you're like, why did we recap all of this? Well, we recapped all of this so you could understand where the quantum model is actually coming from. So in our quantum model, we're going to have our nucleus. So now we have the quantum model. And this is all modern scientists, because it's no longer one scientist that did main discoveries, that did all this hard work. Now it's a whole bunch of students and professors and teachers working together and went, I think we figured something out. And they came up with the quantum mechanical model, or the quantum model. Okay. Now we see this with different names like the quantum nuclear model, the nuclear quantum model, nuclear mechanical model. I mean, yeah. Anyways, so the quantum mechanical model, inside of this model, the inside is still our nucleus with our neutrons and our protons placed together. Okay. So they're in here, and I'm just using 2 different colors to represent the protons and the neutrons. Okay. Now around this is our orbit. Okay. And our orbitals, which are going to be in the form of lobes. So the first orbital, okay, energy level 1, is in this lobe-like material. Okay. And lobes are like clouds. So these are like clouds. And this first one looks like this. And that's for energy level 1. Then we have the lobe for energy level 2. And that looks like this. Okay. And this is the lobe for energy level 2. And then we have our lobe for energy level 3, which can vary in its form. And that is similar to the rest of these, but it's now thinner outer lobes. And they're going to come out. I'm just going to put these ones in this color so you could see this better. Okay. And some of these actually have another little flat pancake lobe going out like this. And you're like, what is this? We only see this in like shows or cartoons where it shows something weird like this. Okay. These are actually the orbitals. So these orbitals that we see here, these circles, right? They're actually clouds. And these clouds have different shapes associated with them. So these are called lobes, and they create electron clouds. And the electrons are free roaming inside their assigned lobe. So electrons free roam inside the assigned lobe. And or cloud, if you want to call it cloud, or energy orbital, any one of those. Okay, so here we go, the quantum mechanical model. All right, awesome, right? We just built our entire atom through history, all the way from 450 BC with Democritus to our modern scientists, leading to the quantum mechanical model, which is going to lead to wave duality, right? Like what? All right, wave duality. We learned because of the movement in here, they're free roaming inside their assigned lobe. Electrons move both as waves and particles. And this is called the wave duality theory. So there it is, the wave duality theory. Now, because we now know that they're not in orbits like this, they're in these clouds, and these are 3D, by the way. 3D, okay? That means they have dimensions associated with them. We can't just find an electron and say, oh, it's on the left side of the lobe. Oh, now it's on the right side of the lobe. No, it's going to be like, is it in the center? Is it towards the edge? Is it towards the bottom? Bottom center, bottom right, bottom left? Like, where did it go? Okay. So we don't know where the electrons go, and these leads to the uncertainty principle. Certainty principle. Okay. And the uncertainty the uncertainty principle basically says that it is impossible to know both the location and the velocity of an electron at any given time. Okay, you can't know both of them at the same time. So it is impossible to know both the location and velocity of an electron at the same time. Okay. So impossible to know both of those. So what does that lead us with? Well, that leaves us with trying to identify the location of the electron. So we want to identify that location. All right, guys. So let's figure out now how to find the location. Finding the assigned location of electrons. Where'd you go? Where's your house at? Where do you live? Well, electrons live in energy levels, right? And each energy level has sublevels. Sublevels. Okay, it's like saying I live in the Via Complex apartments, and you're like, okay, cool. Which one? Are you in apartment A, B, C? Which one of these buildings are you in inside the apartment complex? And you go, oh, I'm in apartment A. You're like, cool. What floor are you in? Are you in the first, second, or third floor? Oh, I'm in the second floor. Awesome. Now that we know what floor you're in, what direction? Are you on the right side or are you on the left side of the second floor? I am on the left side. Okay, cool. Now what? What number are you in? Same thing here. It's like they're apartment levels, but we're going to label them and call them different things. So let's go ahead and start introducing what everything is. So you're going to see the symbol N. N stands for the principal energy level. Principal energy level. It's the principal energy level. And this energy level are the rows that you see on the periodic table. And these rows are your orbits. Okay? And there is 7 rows on the periodic table. So that means your numbers can range from number 1 all the way to number 7. Okay, so if you look at a periodic table and you go from up to down and you count all those rows, you're going to have 7 main rows. N is equal to 1. That means that that is the closest to the nucleus. That's energy level 1. All right. So we look at these. Energy level 1 is the closest to the nucleus. So when you see these numbers, now you know that this is N is equal to 1. N is equal to 2. Right? My marker isn't really working that well here. N is equal to 3. Those are your energy level ones. So if I ever ask, which energy level is the closest to the nucleus? The smaller the energy level, the closer to the nucleus it is. Okay. So N equal to 1 is the one that's going to be closest to the nucleus. We're going to make a quick little chart. Okay. So I'm going to have energy level here. So energy level. Can't use that marker. Okay. We're going to have electron capacity, That means how many electrons can it hold? Sublevels. And number of orbitals. Okay. So in my first one, energy level 1 can hold a maximum of 2 electrons. Okay. That's discovered by Niels Bohr. Sublevels. It only has one sublevel, and that is called the S sublevel. And the number of orbitals is just going to be 1. Okay, just 1 orbital. And then we're going to have the next one, N is equal to 2, so energy level 2. Things change now, okay? It changes in our periodic system table. So let's... I don't know if you guys can see this periodic table right here, okay, but hopefully you guys have yours. So energy level 1, you notice that this first energy level only has 2 elements. So that's energy level 1, capacity for 2 electrons. And those 2 electrons, it's easy to think of each box, each element box can hold 1 of those valence electrons. So it's only counting the outer. So you would just say 1, 2. 2 electron capacity maximum, sublevels. This is called an s sublevel. You're just going to have to memorize that. And the number of orbitals is just going to be 1. Energy level 2 comes down here, okay? So energy level 2 has the capacity to hold 8 electrons. So there's 6 here, plus the 2 all the way right here. That's a total of 8 electrons. So we're going to write down the number 8. The sublevels that it has, okay? Now I know my the periodic table is kind of flipped on my end. So it actually starts over here. This block right here, these 2 columns, represent the first sublevel, and that's sublevel S. So we have to cross these 2, which is sublevel S. So we have sublevel S present. And then we go straight across and we come to these ones. This is no longer sublevel S because sublevel S can only hold 2 electrons. So we have a new sublevel, and this is going to be sublevel P. Okay? And how many orbitals does each hold? Well, every 2 electrons fit inside 1 orbital. Okay, so 2 electrons per orbital. Let me put this down. Okay. So s orbital can hold 2, so that is going to be 1 orbital for the s. And my p orbital, there's 6 electrons, so that's going to be 2, 4, 6. That's going to give me 3 orbitals. Okay. All right, let's look at another one. N is equal to 3. Okay, and we're going to go all the way to n is equal to 4. Okay. So in n is equal to 3, we could hold a maximum of 18 electrons. What? But you said 2 and 8 and I don't know what. All right. The reason we could hold 18 electrons is because now when you're in energy level 3, sublevel 3, right here, okay, you have the S, right? You have the P, okay? You're like, so where does everything else come from? The transitional elements. So this bumps up 1, and this is also part of your energy level 3 block, these 10 electrons right here. Okay, so it bumps up and adds to your 3rd energy level. So this right here is called the D block, the D block. So now we have S, we have P, and we're going to have the D block. Okay. 1 orbital for S, 3 orbitals for P, and 5 orbitals for the D block. Okay. You know, I like that I started changing the color here. All right. Now we're going to go to n is equal to 4, and in n is equal to 4, it can hold a maximum of 32 electrons. Okay. And it's composed of an s orbital or an s sublevel that has 1 orbital in it, a p sublevel that can hold 3 orbitals in it, a d sublevel that can hold 5 orbitals in it, and an f sublevel that can hold 7 orbitals in it. Okay. Each orbital so these are these right here. So each orbital can hold a mass of 2 electrons. Okay. Each orbital can hold a maximum of 2 electrons. Okay. And each electron has a different spin. So for example, if this is my orbital, I'm going to have an electron spinning upwards, and I'm going to have an electron with an opposite spin. And we're just going to represent those spins with an arrow going up and an arrow going down. And in most cases, we actually do half of these spins. So you'll see half an arrow or something like that. So this is one electron and it has a positive spin, and we're going to say positive 1/2 of a spin. And that right there is also one electron, and we're going to say it has a negative spin. Okay, that means one spins clockwise, the other one spins counterclockwise. Right. So let's talk about our orbitals. Okay, we said we have the s orbital, the p orbital, all the way to the f orbital. And I should have actually made this a little bit smaller. Hold on. I'm going to need some space. That's fine. Okay, so the s orbital is represented by a sphere-like shape. Okay, this is going to be the shapes of our orbitals. The p orbital is represented by a couple of different shapes. Like this. And the best way to represent this is to show it in a little Cartesian graph. We said it has 3 orbitals, so I'm going to draw 3 little graphs right here. And now we're going to draw the shapes. Okay? The first orbital is on the x-axis, okay? And this is called px. The second orbital is on my y-axis, okay? And this is called py. The next orbital is actually on the z-axis, and this is called pz. Okay. All right, now someone's going to ask me, why did I shade one lobe and not the other? Does it matter? It does not matter. That's just for aesthetic reasons, so you guys could see it better. Okay. All right, the next orbital that we're going to do is going to be the d orbital. Okay, and the d orbital, we said, has the d sublevel, and the d sublevel has 5 different orbitals inside of it. Okay, now to save us some time, so let me make this a little bit bigger. 4 of these orbitals are almost the same. Okay, they're almost the same. So I'm going to draw one to represent them all. Okay, and in this case, we're going to have an orbital going like this. Okay, and we're going to have another orbital coming out like this. Okay. Remember, I'm only shading one side for aesthetic reasons so that we could see these a little bit better. All right, so this one is called the 4-leaf clover shape. This is known as a pacifier shape. And actually, I'll write those names down in a second once I'm done with all these shapes. So there is 4 of these, and the lobes just alter within which axis that they're in because they're 3D. So you're going to have these d orbitals. It's going to be like dxy, dxz, dyz, those kind of things. But just think about that these orbits can be in different spots. Do you really have to know all of that? No, you do not have to know all of that. Not until you get to organic chemistry. Okay, so for right now, no worries. You're good. All right, the other shape, because this is only 4 shapes, is the pacifier shape. And in my pacifier shape, it literally looks like a pacifier. You have one extended lobe, and then you have a squished lobe, but it's not actually squished, it's just on a flat plane, okay? It's on a different plane, so it looks like a flat plane on the side. and then one tiny little lobe, all right, here at the bottom, okay, giving it this pacifier kind of look. So let's write their names down. This one right here, we said is a spear-like shape. The P sublevel are dumbbells. Okay, so these are like our dumbbell shapes. The D sublevels, we're going to call it the four-leaf clover. So the clover and the pacifier. Now we got one more of these to go, and that is the F sublevel, which we said there's a total of 7 sublevels. Now these ones are extremely complex to draw, but we left with the pacifier here. So guess what we're going to have now? The shape is going to be the double pacifier. So you're going to have a double lobe flat planed pacifier. Okay. I'm going to use 2 different colors to show this. Okay. Okay, so there is one part of our pacifier, and then you're going to have your top lobe, and you're going to have your bottom lobe. Okay, so some sort of complex lobe here known as the double pacifier. Now, I'm not sure if you guys can see those, so I'm just going to. All right. So since we had a double pacifier, what do you think the next one's going to be? The double clover, because we're very creative here with our names. So the double clover started by creating an actual clover, like you would for the D, and then add to it your other clover wherever it might fit. Okay. And now this one is called the double clover. Okay. And there is like, I believe there is 2 of these in some shape or form. Okay. And there's going to be 5 of these for a total of 7 orbitals. All right, so this right here is the shapes of our orbitals. So this is shapes. I keep saying orbitals, shapes of our sublevels and orbitals. So this is just the shapes. Well, actually, yeah, orbitals actually fits because each orbital has a unique shape to it. All right, and now remember, in each one of these, you can fit a maximum of 2 electrons. So you could have 2 electrons in here, 2 electrons, 2, 2. Each lobe can hold, or area can hold 2 electrons, and those electrons could be anywhere inside these 3D structures. Okay, so remember, these are 3D. Okay, they are not flat or planed or anything like that. All right. Now, if we want to continue to go and further try to figure out, well, the quantum mechanical numbers, we can do that. I could actually make a lecture on that later, but you don't need it. It's not tested on. I'm not testing you on it. It's not part of our curriculum anymore. It's been removed, but I can make a quantum numbers video so you can learn it, especially for those going up to general chem and OChem. You're going to want to know your quantum mechanical numbers. Okay. For these, you really don't have to memorize these so much. Just recognize them. You're not going to be asked to draw, but you might be asked to recognize them. Okay. and to tell me how many there is in each. I just realized, not just realized, but I know for me, it always helps to have a visual of what we're talking about so that I'm not lost, okay? So these energy levels are actually shapes, right? And we can understand how this has less energy and something like this has tons of energy flowing through it. All right. Okay. So now that we have that, let's continue on a little bit more in finding where our electrons are at and located. Okay. So we're going to go through energy diagrams and then electron configurations. So let's write in energy. Because this chapter is all about energy. Okay. So if I start at the bottom, this is going to be considered low energy. And actually, let me just quickly do this. Low energy to high. And this is going to be high energy. Okay. So starting at the bottom here, this is where we have energy level 1, sublevel S. Then we're going to move up to energy level 2, sublevel S. And we know that energy level 2 also has sublevel P, 2P, 2px, 2py, 2pz. Okay, now instead of drawing these orbitals that we did on this last page, we're just going to put a little line. All right, that little line right here represents the shape. We are not drawing the shapes to put the electrons in them because that's going to take a lot of time, a lot of paper, and we don't got time for that. All right, so we put little lines to represent those shapes. So now we move on to energy level 3. And on energy level 3, we have sublevel S. We also have sublevel P. Now, actually, I messed up a little bit here. Actually, these energy levels should be higher up. Okay, not so low. So there's still 2 P's, but they're slightly higher in energy than the 2S. So these are still my 2 P's. Okay, so I have my 3S, and just like my 3P, it's going to be higher in energy. 3 P's. And my third energy level also has the 3D level to it. Okay, but before I do my 3D level, let's do the other levels. I'm going to put it in a different color so we don't get too confused. We're going to have energy level 4S and 4P. Excuse me. And 4P. And between the 4S and the 4P is going to be my 3D. And D has 5 orbitals. 1, 2, 3, 4, 5. This is 3D. Okay. I should have actually done different colors for all of these. All right. Now, continuing on, 4, remember N equals 4 has an S, a P, a D inside of them, right? And it's also going to have an F sublevel. But we don't want to get super lost yet. So let's go ahead and write our 5S and our 5P. 1, 2, 3, 4, 5P. Okay. And now we could actually do our 4D, which is going to be somewhere up here. 1, 2, 3, 4, 5. This is going to be my 4D. And we could, can we bump it up a notch yet? Yeah, we could bump it up the notch and actually show our 4F. 1, 2, 3, 4, 5, 6, 7. 4F. You notice how they're going in this diagonal manner, increasing in their energy level. So here we had 2S, and 2p, right? So slight increase. So it goes up in a diagonal-like fashion. So we have our 5p. From our 5p, you're going to see our 5d. 1, 2, 3, 4, 5, 5d. And then you're going to see the 5f. 1, 2, 3, 4, 5, 6, 7, 5f. And this literally continues on all the way until you get to your 7. So you have 6s, you're going to have 6p, 1, 2, 3. You're going to have 6d, 1, 2, 3, 4, 5. And you're going to have 6f somewhere up here. Okay. It just goes on. Okay. That's our energy levels. And that's to show how it increases in energy. Some people can use this very well to write down all their electrons. I'm not that good at using this one. Okay. I mean, I can do it, but I don't like it. It's too complex for me. What I like to do is electron configurations in a different way. So my electron configurations are going to be a lot simpler than having to draw this and showing all my electrons on that. Now, if you like this, if this is something you can do, like you're very aesthetic, you have the ability to make things look good, and you have that patience, by all means, you go and you do you. All right. To me, I like the easier path, and in this case, the electron configuration is going to be my easier path to success. So let's start with an example and show what everything means. I'm going to show you a simple electron configuration. And this one is actually not the full configuration. It's just a location kind of thing. All right. So let's talk about what all of these mean. The number 2 represents the energy level. So it equals to N, right? Our energy level. That's the same as what row something is in. So what row is it in? The row it is located on. And obviously when we say location, we're talking about the periodic table. The P represents the sublevel. Okay. So the sublevel is which block is it in? Which block on the periodic table? Kind of like saying, are you on apartment A, B, C, or D? And I'm saying I'm in apartment P. Okay. The number 3 is the number of electrons in that sublevel. And basically, you could actually count and figure out which element you're talking about by looking at a periodic table. Okay. So this is the basics of an electron configuration. Now, if you guys open up your periodic table, let's try to find it. We're saying that we're in energy level 2. Now, I know this is hard to see, and let me see if I can Google periodic table and show you guys that way. Okay. Okay, perfect. So here's our periodic table. And what I want to show you guys is, okay, energy level 1, right here, that's our S block. Now we're going to look for energy level 2. So remember, we're 2p3. So all of this in this corner is considered the S block, right? That's the S block. So I'm in energy level 2. This is S block. I don't want that. I want the P block. So I'm going to continue going. This entire block here on this side is considered the P block. Okay, I wonder if we could do this by Okay, perfect. So all the green is considered my P block. The yellow is the D block, the transitional elements, and the blue is the F block. Okay, the F block. All right. So I'm going to be in 2P. Here's 2. This is P. So that means I'm talking about any one of these elements. Well, which element are we talking about? So, like, which apartment do you live in? I live in apartment number 3. 1, 2, 3. The element that we're talking about for 2p3 is nitrogen. Okay. Isn't that pretty cool? I think that is actually really cool to figure that out. If I was talking about 2p2, that would be carbon right there. Okay. 2p6 would be neon. If I said I have 3s1, here's energy level 3, here's the S block, and this is 1 right there. So I would be talking about sodium. Sodium. Okay. All right. Memorize your electron configuration blocks. It makes electron configuration, like writing them out, so much easier. But now that you guys see this, remember this is S, this is P, D, and F. All right. So we have that information. Let's go ahead and start making electron configurations. So the first configuration that I want to work with is going to be with sulfur. And why do I pick sulfur? Because you know what? When I had COVID, everything smelled like sulfur. Everything. My coffee, sugar, salt, everything. So sulfur was very, very much part of my life. All right, here we go. And we're going to be talking about the neutral atom of sulfur. Okay, and if we look at the periodic table, sulfur is represented by an S. And because it's neutral, there's going to be no charge written up here. Okay, remember if there's a charge up here, then you have an ion. Because it's neutral, then my protons are going to equal my electrons. And looking at the periodic table, sulfur, symbol of S, it's going to have 16 electrons. Okay. Oh, excuse me. So let's go ahead and write our electron configuration. We're going to do something called the long form. And this long form is known as the orbital or arrow configuration. And so I'm going to call it the long form, also known as the orbital or arrow configuration. Yeah, it's just right here. Orbital slash arrow configuration. And usually when something says write the electron configuration of something, it wants the long form. So they also call it the electron configuration just by itself. So this is the long form, okay? If you could do the long form configurations, you could do all the other kind of configurations. All right, so we said it has 16 electrons, and we're gonna start with energy level 1. So actually, this is pretty cool here. Let's see what we can do. Okay, so energy level 1, that's gonna be the first thing I'm gonna write, as a 1s, and remember we're using these little lines to represent the shape that we have, okay? So we have a 1s, and we're gonna go all the way to sulfur, which is here, which is 3s, 3p's. So we have to go all the way to 3p. So we have 1s, from 1s we're gonna have 2s, and from 2s we're gonna have 2p, which has 3 orbitals. From 2p, we're now going to go to 3s. From 3s, we're going to go to our 3p. Okay. And that's where we're going to stop because we don't need to go any further. It's located right there. Right. So now we're going to go ahead and fill in our electrons. And as we learned, electrons have that opposite spin, and it's 2 electrons per orbital. So in this first one, we have 16 electrons. It's going to fill with 2. Okay. Now there's some laws for electron configuration. One of the law is you always start with the lowest energy level. I am not going to automatically start filling my electrons here or anywhere that I want. Like a video game, you always start in level 1. Okay. Once you're done with level 1, boom, bump it up and move up, right? Okay. So we have 2 electrons out of 16. I now have 14 left. I'm going to move on to the next one. 1 electron goes up, the other spins down. I'm done with that energy level. Or sorry, I'm not done with the energy level. I'm done with the sub-level. So now I'm at the lowest sub-level. I'm going to jump to the next highest sub-level. So 1 electron up. The next rule says that you could only have 1 electron per orbital before, or you must have 1 electron per orbital before you add another electron in it. So what that means is I cannot go ahead and fill that first orbital up. I cannot do that. So what I'm going to have to do is put another electron on each of those orbitals first. And then if I still have electrons left over, I will fill it up. And that has to do with bonding. Okay, do it the correct way and you won't mess up. Okay, if you start being lazy or complacent with this, you're going to end up messing up your electron configuration and you're going to get asked questions about bonding, valence electrons, and you're not going to have the correct answer. Okay, so make sure you fill 1 electron per orbital first before you pair them up together. Okay. All right, now we're going to move on to the next energy level. We've used up 6, 8, 10 of those electrons. We have 6 more to go. Okay, so I'll put 1 electron here. Now, most of us are going to say, well, why am I not putting it in the P's if we can't have, if we can't pair them before filling the orbitals? Well, remember, P is at slightly higher energy level than S. And the first rule is you have to fill the lowest energy levels first. So there you go. That's filled now. We have 4 electrons left to go. I'm just going to count to verify. 2, 4, 6, 8, 10, 12. We have 4 electrons left to go. So I'm going to go ahead and put 1 in each orbital first before I go and fill. And that's it. I don't have any more electrons, so it ends right there. This is 3p, 1, 2, 3, 4, 3p, here's p, 1, 2, 3, 4. This represents the neutral atom of sulfur. And I'm going to put a 4 here, and we can actually start filling this up. 2 fit here, 2 there, 6 here, 2 here, and then a 4 there. So that's my electron configuration. The first part is called, so this top part is actually the arrow notation. And in this bottom part is actually the electron configuration. And together they make this beautiful thing that shows our electrons, what spin they have and everything. Now you're going to say, why can't I just do the 3.4? Why do I need the arrows? Well, if you just give me the electron configuration right here, the 3p4, and you don't do the arrow notation, and I say how many electrons are available for bonding, most of you guys are going to say 4, but that would be incorrect. Okay. If you look at the arrow notation, these electrons that are by themselves are the ones that are available for bonding. These are our bonding electrons right here. No electron wants to be by itself. It wants to bond, it wants a pair. Okay, so they're going to be our bonding electrons. So these here are the bonding electrons. Well, okay, they're my bonding electrons. So how many bonds can sulfur make? The answer is 2. Sulfur can make 2 bonds. We now know that sulfur can make 2 bonds. Right? Now, if I say, what is the location of sulfur? Where is sulfur located? The location of sulfur is this 3p4. So this part represents the location. That part represents the location. I really don't know if you guys can see this yellow that well. So okay. Those are the bonding electrons. This is the location. And now I'm going to ask for one more kind of notation, and that's going to be the noble gas notation. And noble gas notations are actually kind of cool, especially when you have really, really long elements, like, for example, silver or lead, right? You really don't want to do the full notation for that. So you want to do the noble gas notation. And when we do one of these, we can easily figure out our noble gas notation. You're always going to start with the greatest energy level, right? So in this case, it's energy level 3. So that means I get to skip all of this. How? Well, I'm going to look where 2p6 ends. And 2p6 ends here with neon. It ends here with neon. So I'm going to put neon down in brackets because I'm saying I'm going to include neon, everything up to neon in this case. And then I'm going to end it with where I need to end it at, which is my location of 3p4. So I get 3s2, 3p4. Actually, should have done 3. 1, 2, 3, 3p4, 1, 2, 3, 4. And that is called the noble gas notation, right? I basically took everything out and just wrote an element down in its place. All right. We'll do one more example with the electron configurations, this time using an ion as an example. And we're going to use the ion of sulfur because sulfur was our first example. Remember, sulfur has 16 electrons when it's neutral. But if I gave you sulfur with a -2 charge, how many electrons do we have now? You're going to have 16 plus 2. Remember, they're both negative, a negative and a negative, right? Added together is still a negative. We get 18 electrons total. Okay, so now we're going to do the configurations for sulfur with a -2 charge. All right, so a couple things to note is that our original location for sulfur neutral was 3p4. Now we have added 2 electrons, so we're going to end at 3p6. And that's really cool to know because now we could just say, all right, maybe I just want to do the noble gas notation. And in your noble gas notation, you would do neon. And you have 3s2, 1, 2. And you're going to have 1, 2, 3, 3p6. 1, 2, 3, 4, 5, 6. So this right here represents sulfur with a -2 charge. Okay. Now, what if it was a positive charge? Oh, by the way, before we actually move on, this right here, because it ends in 3p6, that is where argon actually lives. That means that the ion of sulfur with the -2 charge has the same configuration, same electron configuration as argon. So you're like, all right, cool. What does that mean? Well, that leads to a keyword called isoelectronic. Isoelectronic. Okay, that means they're going to start behaving the same electronically. All right, so sulfur is now going to start behaving like more of like the inert argon. Okay, it's not going to want to move. So this means the definition of this is that it's an atom with the same electron configuration as another atom. And the way you get to that is through ions, right? So atoms slash ions, because that's the way you actually get to it, with the same electron configuration of a different element. Okay. So sulfur ion is isoelectronic with the argon ion. All right, we'll do one example of the positive, and that's going to actually end this chapter. So let's do magnesium, okay? And we're going to do neutral magnesium and then magnesium with a +2. So magnesium is, okay, it's located right here. Okay. So this one's neutral, so it's just Mg, and magnesium has 12 electrons. Okay, so remember we're going to start with the 1s, the 2s, the 2p, and the 3s. And that's where actually where this stops. It stops at the 3s. And I put in our electrons. 1, 2, 1, 2. Go up, 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 down, down, down. Okay, so we have 1s2, 2s2, 2p6. We boost 10 out of the 12 electrons. 1 electron goes up, 1 electron goes down. Okay, magnesium has now completed, we have now completed the magnesium's electron configuration, okay, with this. Now, note that the 3s still has the empty 3p orbital available to it, right? So it still has an empty 3p orbital. So because we can look at this and go, well, how does it bond, right? Well, things move around. They move around. And the other thing is with our ion, +2, that means that we're actually going to lose 2 electrons. So you're going to end up with 10 electrons total. Okay. So this is going to look like 1s2, 2s2, 2p6, 6, 7, 8, 9, 10 electrons total. 1, 2, 3, and then it's going to be 4, 5, 6, just like that. And that's going to give us our electron configuration for magnesium with a +2 charge, which means that it lost 2 electrons, 1, 2, and it's now going to be isoelectronic with neon. It's going to have the same electron configuration as neon. All right, and then we're going to get, okay, cool. So how do they even bond? Because there is no available bonds right here that I can see for it to do anything, right? Well, one more time, remember you have empty orbitals. And what actually ends up happening in some cases is that our electrons um, bond in a way where they go to a different atom, right? They're like, hey, go ahead, take my electron, right? So metals love to give away their electrons. Non-metals love to take electrons, right? So it would actually give away some of its electrons so that it could bond. Some of these electrons will actually try to jump energy levels, okay, to create those extra bonding moments, right? So jump energy levels to create extra bonding moments. All right. This kind of ends the chapter on electron configurations. I am going to make a video on quantum numbers and another one probably going over some sample problems of this because I know it can be a little bit tough and confusing. All right. Hope it helped. Ciao.